Okay, so let's look at using the discrete Fourier transform or the fast Fourier transform, the FFT, to do spectral analysis of a signal. Remember, our goal here is to find FM, the maximum frequency, the highest frequency component in a given signal. So we use the FFT to find the frequency content of the signal, and then the highest frequency is our FM. So to get to the discrete Fourier transform, DFT, or the fast Fourier transform, FFT, I'm going to skip most of the theory. But if you started with the Fourier series, which we looked at in the previous video, that works over a given range of time. So if we let that range go to infinity, that makes the frequency go to 0, and that gives us the Fourier transform. Take the Fourier transform and change it over to discrete math with discrete samples, gives us the discrete Fourier transform. And then the fast Fourier transform, FFT, is an efficient algorithm of the DFT. So like I said, I'm skipping a lot of theory. It is in your book. But the big takeaway is that discrete data is very easy to gather, and the FFT is very easy to use because it's built into every math program that you probably would want to use. So what we give the FFT is a column of data like this. So a set of measurements of our signal versus time. So that's really easy to gather. We feed it that column and we get a column of frequency response. Here's an equation for the DFT. It gives us each row of the DFT based on this calculation. So it's a sum over all of the measurements of g, little g, and there's a complex exponential term up here, and that gives you each row. So if you give a column of data like this, you can calculate each row using this equation. The FFT is more efficient than this because it doesn't have sums upon sums to calculate it. And there are some limitations, but they're not really important because most of the packages you'll use will either switch to the DFT from the FFT when they need to, or they'll prompt you to make the right decisions. Things like the number of samples has to be a power of 2 for the FFT. But this is built into MATLAB, it's built into Excel, it's probably built into your fancy calculators. So it's something that you normally just apply. So the input to this function, the FFT, is our column of measurements. So again, over here on the right, function of time. And then what we get out of the FFT function is a column the same size, same number of rows as our input, with complex numbers. So the FFT, we need to know the sample rate and how many samples we've taken. The interval between samples, delta t, is 1 over fs, if fs is in samples per second or hertz. A really important number to remember here is the delta f. This is the frequency change between rows of the FFT answers. And you need that in order to apply the sampling theorem. And most calculators have the FFT built in, but they don't do this part for you, so you have to remember that. Here's an example of some data, and there's another video that shows how I gathered this data using Excel. But again, what we're starting with is this column of data, so little g. It's voltage versus time. So here's time, here's voltage. It's indexed with K, and it starts off with 0 times delta t, then 1 times delta t, and 2 times delta t. So it's evenly spaced in time. And so we just give it this one column of data to the FFT function, and what we get is this column of data. The capital G is the fast Fourier transform. And the things to notice are its complex numbers in general. So there's a real part and an imaginary part. A couple of other things to notice are it does repeat. So this number and this number are the same. This number, that number are the same. It repeats kind of in reverse order for the bottom numbers. So it's very simple. It's one function call in MATLAB to get a column of data like this to a column of data like this, but the interpretation takes a little work. So here are some tricks of the FFT in order to use this again for the sampling theorem. So the first thing is this is the frequency of each component of the FFT, each row. So the frequency is k times the change in frequency delta f, and delta f is from this equation. So you have to calculate this column yourself, and then we'll graph g versus frequency. The other thing to remember is that half of the data is aliased, so all of these bottom rows are useless. So anytime our sample rate here, we can see we're sampling every 1/10 of a second, so our sample rate is 10 Hertz. So anything over 5 Hertz is aliased by the sampling theorem. So in the frequency column here, when we're above 5, it's aliased. That's always the bottom half of the FFT data. So don't use this data. Throw it out. The last thing for our graph, it's hard to graph a complex number, so we typically graph the amplitude of these complex numbers, or the magnitude. So the complex magnitude is usually written with absolute value signs, and it's just the square root of the real part plus the imaginary part squared. ABS in MATLAB will do that for you. So with that, we have frequency on the x-axis, magnitude of the FFT on the y-axis. We throw out the alias data, and we get a graph that looks like this. So here's our graph. We've got frequency on the x-axis from that column that we made. This is the magnitude of the FFT data on the y-axis. This was created with a sine wave, so we can see it's got one major dominant frequency here, and then it bleeds off into the other frequencies. So just like the Fourier series analysis, we end up with amplitude versus frequency, and at some high frequency, we say that the amplitude is too small to care about, and that frequency is the maximum frequency that we care about. So somewhere in here around maybe 5 Hertz on this signal, we can say we don't care. Because we started with sampled data, you really have to use a fast system. So you'll probably go out and rent a really fast data acquisition system for this experiment to make sure that anything interesting is captured and you're not already starting with alias data. And then again, it's your judgment on what small means. And we can use things like the resolution of the analog to digital converter, and we'll see that later on in this class. So the FFT is a really powerful analysis tool that finds the frequencies of the dominant components of a signal. So we use that for the sampling theorem, but we can also use it to find frequencies that are in a signal in general. So frequencies in a signal can tell you things like how fast an engine is spinning based on the sound. You can find the musical notes, so most things like guitar tuners are based on something similar to an FFT analysis. Find the frequency of the note that you're listening to. And there are lots of other interesting quantities you can find with the FFT and the frequency components of a signal. These kinds of algorithms we won't go into in much detail, but they are used in lots of other ways in engineering. Things like data compression, because you can come up with an accurate curve fit or a model based on the frequency components of a signal. Noise reduction, where if you FFT the signal to find the frequency components, you can zero out certain frequencies and then turn it back into the original signal with an inverse FFT. And things like pattern matching are used, where if the FFTs match, then you have a good idea that your signals are similar to each other. So I hope you enjoyed the FFT and you will get to try it in Excel or in MATLAB as homework.